Welcome to this video on structural segmentation. My name is Mark Jenkinson, and in this video I'll be talking about a tool that we have for segmenting tissue types within the brain. That is for delineating where the different tissues are. As you can see in the image down in the bottom right there, we've color-coded the three main tissues that we're looking for in the brain. That is grey matter, white matter, and, for lack of a better term, CSF, cerebral spinal fluid, which we're going to call a tissue for these purposes. And that's the three main sort of gross anatomical categories that we're going to use to split up all of the different locations in the brain. The tool that we have within FSL for doing this is called FAST, FINRIB's Automated Segmentation Tool. And that's what this video is going to cover. The input that we need for FAST is just a single T1 weighted image. That's all that it requires. And what we would do normally to start with is to brain extract that. And that's particularly important for doing segmentation because there are many other types of tissue outside of the brain. There's muscle, there's fat, and so forth. We don't want to segment those, and in fact they're quite confusing because the intensities of those are quite similar to the intensities of different types of tissue within the brain. Once we've done our brain extraction, then all we're going to do is concentrate on the brain, and everything which is inside the brain is going to be assigned to these three different types of tissue which we're typically looking at for healthy brains. We're also going to incorporate a measure for bias correction, and that's going to solve one of the artifacts which we often see due to the fact that the RF coil is not uniform, is that areas of the image are brighter or darker than they should be. And so we're going to incorporate that within the FAST model as well. So as I said, our input is normally a single image, normally a T1 weighted image, but it doesn't have to be. It could be a T2 weighted image of proton density, as long as you've got a good contrast between the different tissues. And by that I mean that there's a clear distinction in their intensities. You can look at the image and you can see that there are different levels of grayscale associated with the different tissues. But there's also another option, which is called multi-channel, where we can take several inputs at once. And in that, we can feed it, say, a T1 weighted image and a T2 weighted image and a proton density. They all have to be aligned beforehand. We use our registration tools to do that. They all have to be brain extracted. But once we've done that, then we can actually put them all in together and they can all contribute to the segmentation. Typically, we don't do that. Typically, we find that actually a single T1 weighted image for a healthy subject works totally well, and we don't actually benefit much from putting the other channels in or the other different images. Where that is useful is where we might have some kind of pathologies, but FAST and this kind of tissue segmentation is limited in what kind of pathologies it can easily deal with. And so this is an option which is sometimes useful, but not that often. Most of the time we're just going to work with a single T1 weighted image, and that's what I'm going to talk about for the rest of this video. So the idea behind tissue segmentation using this image is that we're going to base it on the intensities. Because if you look at that image, you can see the different intensities. The CSF is darker than the other tissues, the grey matter is in between, and the white matter is the brightest. And we can look at that image in the way of a histogram. So the histogram is what you're seeing in red there. That's just a count of the number of voxels at a particular intensity. And we can see peaks according to the different tissues. They're not very distinct, so the grey matter peak is probably the easiest to see, and there's a white matter peak just on the right of that here. And then CSF has barely a peak. It's much smaller and much broader down here. And the fact that they're not easy to see reflects the fact that this isn't an easy problem to solve. If they were very clear and very distinct and separate from each other, then this would be a really easy problem. But it's not, because MRI, we've always got a lot of noise in the image, and that, amongst other things, is what makes it hard to separate these tissues, and why we have a particularly sophisticated tool for trying to do it. The way we're actually going to do it is with a mixture of Gaussians. Now, you don't need to understand all the details of how this works, but some understanding of the concepts behind it is helpful, particularly in understanding what might go wrong and some of the options which you can change in order to improve your segmentations. So the basic idea is that we're modeling each tissue with a particular Gaussian. That simply means that the intensities that we expect to see for that kind of tissue are distributed according to that Gaussian. And then the histogram is simply the sum of those three Gaussians. As I said, if they were really narrow Gaussians and they separated really, really well so that they didn't overlap, then this would be an easy problem. But it's not, because of things like bias field make it harder, blurring induced by the scanner acquisition makes it harder, the resolution and the partial voluming makes it harder, head motion and always noise also contribute to the fact that there's a lot of overlap. What this mixture model does is allow us to, even at this point, assign some probabilities just on the basis of intensity. So if I look at a particular voxel in the brain, like I've got here, it has a particular value of intensity. Here it's 17,203. If I look that up on my histogram with my 3 different Gaussians, I can look at where it is on each Gaussian, and that gives me an indication of the probability, which you can see is pretty much 0 for CSF, very low for grey matter, and quite moderate for white matter. So it's much more likely to be white matter on the basis of this probability model. And that's the starting point that we have. But that's not all that we do. Because as I said, one of the other problems that we run across is bias field. And that's, as I said, due to the RF coil not being uniform everywhere. If you look at the original image example on the left there, you see that the back of the brain is much brighter than the front of the brain. The bias field is what you see in the middle, that reflects that. And that's what is effectively multiplying what would be a nice even image, like you can see on the right-hand case in the restored. In this case, the restored image is actually just our original image divided by the bias field. So if we know what the bias field is, we can make a restored image which looks much better. What we start off with is the original image. And so what FAST is going to do is that it's going to also estimate what that bias field is as part of the process in order to help the segmentation. But these two things are interrelated. The intensity might be changed by the bias field, or it might be changed by the fact that it's a different tissue type at a particular voxel. And we need to be able to separate out those two different effects. Thankfully, the bias field is nice and smooth, whereas the anatomy can change from voxel to voxel. One voxel could be grey matter, the next one could be white matter. So those changes are much more sudden. The bias field changes are much slower as we go across the image. And that's the way that we can differentiate between the two. And that's what FAST does as well. If you look at the histograms associated with the original image before we've done any bias field correction and the restored image after we've done the bias field correction, you can see the dramatic impact that it has on the histogram and our ability to separate and clearly see the different peaks. It hasn't got rid of all the overlap, but it has really helped us a lot. The other thing that we're going to use is we're going to use information about the neighbourhood. Because one of the things about noise is that it's just as likely to occur in any configuration, whereas the anatomy is likely to occur in regions which are connected together. So the top example on the right here is a likely configuration due to anatomy because all of one tissue type is together and all the other tissue types together. The one at the bottom is much less likely because it's all interspersed, whereas noise is just as likely to occur in the different configurations. And so we can separate out what is a likely high probability configuration for the anatomy from one which might just be driven by noise. And that can also help us get a better segmentation. So we're going to use both aspects. We're going to use the intensity coming from the mixture model, and we're going to use this spatial neighbourhood information, which comes from a Markov random field or an MRF. You don't need to know any details about what that is, just that it incorporates this neighbourhood information. And then because we've got two sources of information, we need to combine them together. And so we have a formal equation which links them. We have a probability which is related to the intensity-based probability from the mixture model and some weighted amount of this spatial neighbourhood probability. And this weighting factor, beta, is user adjustable because we don't know what the right value is. We have a default value which we put in, and that's reasonable for fairly typical scans with typical SNR and typical resolution. But actually there's quite a wide variety in what you might get. And these things change a lot depending on how scanner operators try and optimize their scanner in terms of the amount of time they're going to spend getting your structural image and the resolution that you're trying to aim for. So this is definitely something which is worth adjusting on a case-by-case basis, or at least adjusting for a particular study. Once you've got it tuned for a particular type of protocol, particular acquisition, then actually you can keep the same value for all of them. It's likely to be a good value. You don't have to change it per subject, but it is useful to tune it every time you have a new sequence. To give you an idea of the effect it has, here are 4 different segmentations for the same brain with different beta values. If we have beta equals 0, it's actually throwing away all that neighbourhood information, so it's not using it at all. And then when we go through to beta equals 0.5, it's using it much more strongly. Beta could go even higher than that, but you can already see the effect here. If we zoom in a little bit more, it's even more obvious. When beta equals 0, we actually see that there are sort of many isolated dots which occur within the white matter, and they're unlikely to be true anatomy. However, if we go right up to the beta equals 0.5, we've got rid of those sort of noisy dots, but actually we've started to cause problems in the cortex. So if you look at these areas, then actually you can see that it started to close in those sulci by actually filling in the CSF and getting rid of that. Because when the spatial neighbourhood information becomes more important, it would actually prefer everything to be the same and all the neighbourhoods to be the same tissue. And if you keep making beta higher and higher, eventually it is going to make the whole brain one type of tissue and effectively ignore the information coming from the intensities. So obviously we need some kind of trade-off. And there's a nice middle ground somewhere in here. I can't tell you what is absolutely the best. I would typically probably favour beta around 0.1 in this case, because it seems to be mapping a little bit better onto what I would expect the cortical ribbon to look like. So that the cortex, you can actually see the CSF within the sulci a little bit clearer. But that will depend a lot on the kind of acquisitions that you've got, the kind of resolution, and what's most important to you. And maybe it's not that, maybe it's something in the subcortex which might require a slightly different tuning. So just be aware that this is one of the parameters that you can tune to try and optimize the performance for your particular acquisitions and the task that you're trying to do. Now, everything I've talked about so far is in the context of doing something fairly simple. That is, I'm trying to decide for each voxel whether it is grey matter or white matter or CSF. That is, whether it is 100% grey matter or 100% white matter or 100% CSF. Now that's true for many voxels in the brain, but certainly not all. There are plenty of voxels where actually they're a mixture. There's a partial volume mixture of things where they're on the borders between different tissue types, or even when they're in some of the subcortical structures where actually there is a mixture of axons and cell bodies, which is different from what we would get in the cortex. So it is actually anatomically somewhere in between the grey matter of the cortex and the white matter and the deep white matter. So what we've been talking about before is a hard segmentation, where I try and force each voxel to be only one thing, 100% of something. The better model is a partial volume model, and that's trying to estimate what fraction of the different tissues do I have at each voxel. So I might have 40% CSF and 60% grey matter and 0% white matter, or I might have some other combination. That's what the partial volume model does, or the PVE, the partial volume estimate, tries to get at how much of the different tissue types there is in each voxel. Because we have 3 different tissue types that we're looking for, we actually create 3 different maps. The partial volume estimate for CSF, which is what you see on the left there, for grey matter in the middle, and then for white matter on the right. And you can see that actually there are areas which are completely solidly white. You know, if you look in the deep white matter, for instance, or in the middle of the cortical ribbon. But actually, if you look at the edges, you'll see that they taper off to some grey value and then go down to 0 outside. And that's important for us to get accurate estimations of the volume. It's a much better model because it reflects the reality better, and it also gives us a better ability to estimate the precise volume of things like the amount of grey matter within the brain. So this is the model that we favour. This is actually done after we've done an initial hard segmentation. We use it to refine that as a starting point to get our PVEs, which is really the thing that we're interested in getting. So just to see how this all fits together, there's actually an initialization even for the hard segmentation, and that uses a particular algorithm called tree k-means. You don't need to know anything about that. It's a rough algorithm. It gives us roughly where most of the white matter is and most of the grey matter and so forth. It's not accurate on its own, but it is useful as an initialization. And then most of the time it's spent in this second group, doing an iteration between bias field estimation and segmentation. Within the segmentation, we're updating the elements of the intensity model, our mixture model, and the MRF, and calculating that and going around and around that loop, refining the bias field once we have an idea of where the tissues are, and then refining our estimate of where the tissues are based on a restored image using the updated bias field. And that's something which needs to be iterated because they are both interrelated. Then after we've got that and we've got our hard segmentation, we move on to the partial volume model step at the end. That actually has its own separate MRF, which controls the partial volume mixtures in a slightly different way. The effect of that is much less, and so that's normally not a parameter that we have as our go-to parameter to adjust. We would normally adjust the MRF within the main loop as the one which makes the most difference, but it is available to adjust the MRF on the partial volume model or the mixel type as well. And then finally we get our PVE, or our partial volume estimate. Something else which is worth talking about is the use of priors. So you may have come across this idea of priors being information that we have before we look at our particular images. They're based on things like atlases or averages across populations. And it tells us, for instance, where do we typically see CSF within a brain image? And if you get an atlas up, you can find that kind of information out. You can get probabilistic information on where you would find these things. And that can be useful. But actually, it can also bias you. So if your model, the atlas that you've used to get your prior information, or whatever the source is that you've got your prior information, is derived from subjects which do not fit the demographic of the subjects you're trying to segment very well, then actually that can give you a bias. So for instance, most of the atlases that we have are generated from young, healthy individuals. If you're using that to segment a very old or pathological brain, then actually the ventricles are going to be a lot smaller than they are in the brain that you're trying to segment. And so that CSF prior can actually give you a bias on where it's going to find CSF within that brain. And so for that reason, we generally turn it off. We do not recommend priors by default. They can be useful in circumstances where the images are hard to segment, and that's normally because there's problems with artifacts or signal to noise or resolution. And in those instances, the priors are there and they're an option to be used. But again, it's important to try and match the demographics of where the priors came from and the subjects that you're trying to work with. If you're looking at deep grey matter, we have another tool called FIRST, which we will talk about in a separate video in order to actually delineate the deep grey matter in a better way than we can with FAST. And so to give you an idea of the options that are available within FAST, there's a bias field smoothing, a -L, which controls how smooth the bias field could be. That should be less smooth on a higher field scanner and with more coils in the head coil array, and smoother on lower field or with less coils in your head coil array. The MRF beta, again, you've seen the effect of that and how we can alter that in order to improve our segmentations. And we would definitely recommend looking at that the first time you use a particular sequence of a scanner. And the number of iterations that you do through your main loop. They all have a fairly substantial impact and are worth looking at as main options to vary your segmentation result. And also, if you're not happy with the output of FAST, there are other alternatives. If you're interested in deep grey matter, then you can look at FIRST, because that's a tool specifically for looking at some of the deep grey matter structures. But there's also another tool called FSL and NAT, which allows you to do brain extraction, bias field correction, and segmentation in a different way, so that it is optimized for trying to work with some difficult images, which include things where there's a lot of bias field. But it is an alternative, so we would normally recommend starting with FAST, but if you find that the results aren't as good as you want, then we would definitely recommend trying FSL and NAT. And so in summary, we've looked at FAST, which is a tool for doing segmentation of different tissue types. Typically we use a single T1 weighted image, although multi-channel is an option. We're separating into major categories of gross anatomical tissue, that is grey matter, white matter, and CSF, which we're calling a tissue. And it models and corrects for bias field. In fact, FAST is the tool that we use in order to do bias field correction. So if all you want to do is bias field correction, you would still use FAST. It will, as a consequence, also do tissue type segmentation, but you don't need to use that. This is the single tool that we have, which is used for bias field correction. It combines intensity and neighbourhood information together, and you can see that there's a parameter for adjusting that. Partial volume estimates, or PVs, are the most useful things that it outputs, and they're the most accurate for volume calculations. You can use priors, but because of the bias that they can potentially cause, especially when the demographics that you use to create the priors are not the same as the demographics for the subjects you're trying to segment. So for that reason, it's not the default. And there are several adjustable parameters that you can use to optimize the output, and we would strongly recommend that you do explore those, especially if it's your first time using FAST, and also whenever it's the first time you're using quite a different sequence.